Okay, let's get started. Are you guys having fun still? Okay. As you see, it's a little bit different from the first two labs, but hopefully you have a real feeling of launching the control hijacking attack against actual software. Although many of them were toy, right? Today we're going to talk about how to utilize Pwntools. Could you close the door? Last week we introduced basic concept of the Pwntool in a way that instead of writing everything in the command line, you can still utilize some of the Python code. So I like to demonstrate that we can utilize the Pwntool even further, so that even for the remote executions and remote exploitations, you can still utilize the Pwntool. Particularly, I like to demonstrate how to write reliable exploitations by using this tool in this class as well. This is the scoreboard. A lot of students actually spending a lot of time solving most of the challenges pretty well. So I'm pretty happy about what we are doing right now. But don't try to compete with the whatever high performance. Just focus on your face. But again, I really recommend you spend time on solving all these challenges if you're excited about these subjects. But do not go beyond whatever 7 challenges per week as well. We have a deadline next week, but if you have trouble solving most of the challenges, come to the West Station again. If you haven't solved the rest of the challenges, these are pretty interesting ones. Like Lec04, basically you cannot reach the return point, return address, what we can do about. The rest of the challenges really allow you to overwrite return address as it is. In fact, it's pretty easy. You have to decide where to put your shellcode and how to figure it out the return address of those shellcode as well. So Lec04 need another step of reasoning about how to actually exploit, leverage this vulnerability so that you can lead this vulnerability into control flow hijacking attack. And flow vindicated is a little bit different type. The shellcode itself can be obfuscated or XOR with simple schemes so that you actually need extra step to decode or encode your shellcode when you're injecting your shellcode to the target binary. Upside down is a very interesting one. If you think about the structure of stack space, in fact, the reason that we have this buffer overflow, because we designed the stack space that allow overflowing, right? You can overflow the stack so that we can override either return address or anything below the stack. But what if the stack is like upside down? In fact, there's nothing to override if you start overriding the buffer. Say you have a buffer overflow. You ended up writing some spaces that we never override, we never use in the code chain. But in fact, if you think about the usage of the stack more carefully, there is something that you can override still by using this, even in this weird architecture. In fact, some of the architecture actually support the reverse of the stack as well, but it's not the completely crazy idea per se. But today I like to walk through these Pwntools by using the correct me challenges that we've been playing with so far. Let's dive into. So let's copy the challenges from our repository, our server. Set the tutorial tool. So I just copied this correct me challenge. In fact, this is not quite different from what I've been working on. So launch the IDE, see what's inside. Oh, I already have the instance. Let's put this binary in different location. Pwntool. I just copy this one here. In fact, this is a binary that you can just interact as it is. In fact, there's nothing special about those. But in fact, there is a weird change in the architecture. If you want to play with this binary in most latest version of the kernel, they don't allow the executions on the stack. So you have to do some massage in order to play with in your local machines. So that I just change the structures of ELF in a way that we can actually launch the buffer overflow attack against this binary. But it's still the same binary. You can just execute, but exactly same in terms of code and data sections. So let's analyze this binary. If you open the binary, so Pwntools, correct me. I just open in IDA, and let's go to the main. This is main function. There's nothing special about this binary. They get the user input from scanf. In fact, scanf allow the indefinite amount of string that you can inject it to the systems. And you compare the buffer with the predefined password key. If everything okay, let's print out this. Otherwise, invalid password. Our task today is to exploit this one, not just getting key, right? Previously, we provide the print key functions as part of those, so you can easily jump to that particular function. But here, there is no such a code snippet you can jump to. In other words, our job is to inject our shellcode that we've been playing with, like we've been playing last week's, and then put it to the crank me challenges so that we can actually exploit. But I like to show you the every single step of writing shellcode, as well as how to exploit them in the server in your local systems as well, right? What would be the first step to exploit this program? What would you do if you have this binary in your computer? Any suggestion? Where is the buffer locate, right? That's one thing we have to do. Most of the hackers just put arbitrary input to here and see if it crash. Pretty good approach and very concrete approach as well. In here, we're going to provide a cyclic pattern of the input to the binary, right? Oh, here it crash. Because it crash, you have core dump that you can analyze. Yes? Oh, yeah. And also make it larger. So here we simply provide the long input to the crank me challenge and crank me challenge crash. So we have something that we can analyze, right? In this case, you can dump the core to locate the corresponding address of the buffer as well as instruction pointer. In this case, instruction pointer is overwritten with this particular pattern. Because we provide the cyclic pattern to the program, you know exactly where the buffer locates and what corresponding bytes in the buffer will be the return address the program is taking, right? How can I know the location of the GAAA? Exactly, you can still look up with the same program. It basically say that in the buffer, with the 24 offset starting from the beginning of the buffer that you just provided, you now have a complete control of the instruction point, right? You can check or double check the exact locations here. Can anyone interpret the comment in this IDA? What is it? There's a buffer. Exactly. Exactly. There are 3 local variables we allocated in this, I'll say, local frame, including v3 and v4 and buffer. Interestingly, the buffer locate at particular locations, this is EBP minus 14 as a hex is 20 bytes. 20 bytes below the EBP, the top of the stack. And if you override 20 bytes, you ended up touching the EBP, the store EBP. And while 4 bytes below, there's your return address you can override. So this nicely matches with what we are observing in previous sessions we tested in dynamic way, right? There's another step that attacker typically do before writing exploitations in terms of what directions I have to take. For instance, this process is very first one that you're gonna do for the later projects, later labs, starting from next week, where we don't provide any executable stack. So you have to think about how to avoid use of the shellcode within the data section, for instance. And all these weird constraints probably help you find a way to exploit the program is really different way. For example, what if I have a security mechanisms that check the existence of buffer overflow before I returning back, right? The simple method that we're going to discuss in next week is called canary method. Is you place the stack canary right before the return address. Is that if you ended up overriding return address, canary will be overwritten as well. In other words, there is a way we can observe the corruptions of a return address even before, right? But here, in order to decide what type of method that you're going to do, here there is a checksec. Where is checksec? This is a utility from Pwntools. So if you provide this one with the correct me challenge, then you can basically know the similar security mechanism, whether the security mechanisms are applied or not. If you see here, each one of those techniques we're going to discuss, but we're going to find out a way to exploit every single one of them as well. So one is relocation with only, this is a very interesting target that we're going to discuss later. And existence of stack canary, whether NX bit indicate whether you have a executable data sections or not. And position independent executable also indicate whether you have deterministic address in your target, so that when you're writing the shellcode, you have exact place instruction pointer you can pinpoint. But if you have a PIE enable, you basically don't know corresponding return address, the program that you're attacking. Then the first step of exploitation will be completely different. For example, even if you have a buffer overflow like those, what if we have a PIE enable in your binary? Even if you override the return address, we don't know where to jump to because the entire memory space will determine at the runtime, which attacker doesn't have. Again, these sequence of security mechanisms will determine the way you exploit the program as well. So luckily, in our system, everything is enabled. It's just no security mechanism in this program. So that we can do live buffer overflow. We can inject the shellcode anywhere we want. As far as we can direct instruction pointer to the shellcode, we can execute. These are pretty good indications of the directions that we can take after simply checking the security of this binary with this tool. So here, you can hijack the instruction pointer with the command line console, but we're gonna utilize a Pwntools. So let's create this Python program. So first we're gonna create the process. Let's just create me challenge. So here we create the process with this particular name, and we can make it interactive so that we can just interact to the program with the typical standard output of this console. Just execute this guy. Then you can provide the password. We say invalid password, or what was the actual password? You can provide the password to the program. You can see all the executions actually happening here. And then, similar to what we did last time, we're going to prepare some payload. right? How many bytes? 24. And then we can put anything that indicate that I really have capability to override the instruction point. This is actually pretty important. When you're writing the exploit, you better debug, like you better, instead of writing everything and tests, you better test incrementally. Because there's so many problems you're going to see, again, including this particular one, which is very simple. You're going to see a lot of problems while you're writing the payload for the exploitation. Here, we just prepared enough buffer and override the instruction pointer. If you run the program, we didn't send. Okay, and then through this API send line, we're gonna provide the payload as a string with the new line character at the end. Then program will accept through scanf and see how it behaves. So program crash, as you can see here, segmentation fault with this particular PID in my local machine. And then you can dump the core and see if your instruction pointer is changed. What would be the next step? You now formulate enough buffer that hijack the instruction pointer. What are you going to do next? Any idea? Exactly. We have to decide where to place our shellcode. And any idea where to put? Stack is one thing. Any other place? What? Environment variable is another popular target, particular local exploitations like workload, right? A workstation. Any other place that you check? This week? Not yet? Yeah, there is another attack vector you can think in this week's challenges as well, right? Shellcode can be anywhere from file names as well. So we're gonna see this one attack vectors in these challenges too. Not just environment variables and stack as part of your input, or you can inject the shellcode through argument and the program name itself. Right? These are the very common attack vector for the local exploitations. Okay. Previously, we create the shellcode by ourselves. Right? We encoded everything with the assembly, pretty nice. But in fact, Pwntools provide very convenient tool like shellcraft. Here, there are a bunch of shellcode that you can utilize off the shelf. In fact, as far as you can specify what you want to achieve, it's a matter of picking the right one. Sometimes you have to manipulate, and I'm going to show you how you can utilize the shellcraft as it is, and I'm going to show you how to modify and extend this shellcode so that we can bypass whatever mechanisms in crank me challenge, right? So the command is shellcraft, nothing special, but if you specify -L, it lists it up all the existing shellcode, off-the-shelf shellcode within the shellcraft. Again, this is part of the Pwntools that we install in our server. Here, there are numerous shellcode that you can access, but the particular one, in this case, crank me challenge, here, if you type file, you can see this is a 32-bit architecture. In this case, we only interested in Intel 3A6. In fact, 3A6 has so many things as well. So we specify the shellcode to the Linux under this architecture. You can specify corresponding architectures and operating system you're working on, and these are the available shellcode that you can see, you can check. As you can see here, there's a shell, SH. This is basically the shellcode that you can use. It launched the bin shell as a result. Or there's a socket, meaning that you can invoke the socket call, likely coming back to your locations. The IP address you can specify as part of this shellcode as well. And there's a fork bomb. You can use the fork bomb in a way that you can drop the number of processes into the target instead of reading proc flag, for instance. In fact, there are many things. You can do the echo, you can cat, or you can read some of the file. And these are the all possibility that you can directly access through this off-the-shelf the shellcode. So the way we can look up is that these are the list, but in fact you can say, if you specify those shellcode that you want to browse, if you type, these are the shellcode. It's formatted in the hexa output, but you can change the output of this shellcode as well by specifying this format argument. Most common approach is that you can print it out the assembly. So you can provide the A after -F. You will see the assembly. This is assembly and shellcode that we're going to play with in this binary. And as you can see here, it's a simple exec call, and they prepare all these arguments slightly different from what we did, but we try to understand this one later. Okay, but this is what basically say is that there is an off-the-shelf shellcode that you can invoke through this shellcraft command, right? This shellcraft command also provide a way to debug or create the final low output. For instance, for example, you can specify the actual the binary of this shellcode. This is a binary output of the shellcode. This is the actual input you can collect and send back to the server. In order to check this binary format is well formed, you can specify this assembly. As you can see here, the sequence of instructions that is well written, well encoded in this byte sequence in here. I specify the row format after -F. So row means the binary output of this shellcode. I simply disassemble the binary in x86 32-bit architecture. It also provides the debugging method or execution method. If you want to execute this shellcode, you can specify -R in a way that it actually compiles this shellcode in the background and execute. In here, it is a shell, so that you can do the shell, any command that you want to execute, even proc flag if you want, right? Similarly, you can do other things as well. In this case, you specify under the Linux in x86 32, I want to execute the shellcode named cat. If you want to see the details of this cat shellcode, you better look up the document and what is this shellcode for. But most of the time, you can see you can pretty easily get the meaning of those shellcode through the name itself. But it say we have to provide the file name. What would be the file name? If you want to get the proc flag, you have to provide the proc flag as an argument to the shellcode. Then shellcode, by observing this argument, they're going to create the shellcode that is appropriate for the job, right? In this case, you can do proc flag. You can provide proc flag as an argument that it run the shellcode with this argument and then actually execute. Oh, it's a set fault. Interesting. Here, if you want to debug those, I like to show you how to debug later too. It's basically if you specify format A, you can see the formulated instructions like those. In fact, it provides a simple way to synthesize whatever user argument as part of those. And then here you can see the proc flag was injected and open. It provides the proc flag string. You put the proc flag string on top of the stack and put the instruction pointer to the open, and it actually invoke and send file to the output. But for some reason it crashed. Let's debug one of those. If you want to debug, like for example, like the previous one, in fact, you can provide a -D. In this case, it launch the GDB sessions on the side. You can see every single step of execution. Here, it stop at the _star, which start with the very first instructions in the shellcode. In this case, push. Okay, let's see how it work. See, So let me explain how this shellcode work at the first place. Okay. Can anyone explain what's going on this 3 push? Can you see the push in the middle? What they're doing? What? Bin SSH to what? They're pushing something on the stack. What do you say? They are the argument to the exec v. Previously, how did we construct this this string? Yes? Exactly, we just appended this string to the end. But one of the hiccup, because of we put it everything in, at the end of the payload, one trick that we did is jump and call back so that we can pop the corresponding address. What's the nice thing about those? You can push everything to the top of the stack, which is a usable space in the program typically, right? Then you get the instruction pointer. And no, you got the stack pointer. And getting stack pointer is very explicit in instructions. You can just copy ESP to the EBX in this case, and you now have a pointer, which pointing to the bean shell that you just push it to the stack. What's interesting about the first push and the way they create the bean shell? Have you recognized anything different or weird? See, first of all, this guy. What's going on? It's not the bean shell. Try to add one more byte. What about the slash in the middle? The directory separator in Linux. Actually, more than that. Then, including, I'll say, you can put like bean shell in like 8 bytes, right? Why they're doing this? And what's a trick that they're putting like 68 at the beginning of this shellcode instructions? And any implication of multiple slash? Yes? What is the ASCII code of 68? What? It's not the separator, it's H, right? Is the end of H? What's the implication of pushing 1 byte? Exactly. So if you push just 1 byte, stack actually operate as a unit, right? Because of the online requirement of the stack. So if you just push 1 byte, the rest of the character will be null. Then what about this multiple slash? What? No? What's the input? Have you tried execute this multiple slash sh? It's actually bean shell. In fact, what about any other program? So if there is a multiple sequence of separator, it really doesn't matter in the Unix standard. They're gonna squash everything to the one. So it's a little bit weird behavior, but this is what people like bear with it for a long time. Just another hiccup, but so that in order to create the 1 bytes at the end with the corresponding null bytes after the push, they create this trick. So then now we have a multiple push, here, so that we really create the bean shell string on top of the stack, and then we got the pointer as a result, right? So let's see how it actually work. So we first push, see how this stack change. We first push about 68 to the top of the stack. Although we say it is integer 68, in reality, right? In fact, there is a lot of preceding zero bytes inside 68. If you consider little endian, you can see the ending characters start with the 0. Right? We just push the last byte of the bean shell to the top of the stack. Right? The next character that we're gonna put through this push operation. See? Because we were reading from top of the stack, now we have dash s sh with the null character at the end. If you push another byte, this 4 bytes of integer to the stack, we finally have bean shell. So if you just dump one string from the top of the stack, now you have a bean shell, which will be the argument of the exec system call. Although, of course, you need this pointer to manipulate the corresponding argument array, the argument vector that is required for the exec-v CVE as well, right? And then we copy this ESP to the EBX, right? Now EBX now pointing to the bean shell string, right? So now EBX contain the pointer to the string, which will be used as an argument later. We just store this particular location by copying the ESP to EBX in this case. Does anyone can explain what's going on in this next line? Until, say, here. What's going on? They push some value, XOR, with the value on top of the stack. And could you comparison? Yeah. If you do XOR with these two values, you're gonna get the string sh, and we manipulate this sh string, and later after these two instructions, we're gonna have sh on top of the stack. Let's see how it works. We push this value on top of the stack, so ESP change. If you do the XOR with these two values, say you're gonna have this one. In fact, this is the bean shell. No, not bean shell, it's a shell. If you interpret this one as well. So we're gonna execute the exec CVE with the sh at the first argument, but inside the argument vector we're gonna put the bean shell. This is how the writer of this particular shell code came up with, right? Then ultimately we're gonna invoke this exec CVE with this argument. Can you see where we are heading? As the first argument of the path, we're gonna do bean shell, which we first construct, and we have EBX pointing to this particular string. So we're gonna pass the EBX to as a first argument of exec CVE, but later we have to create a argument vector, which probably is the next things that we have to do. But we already have a sh string on top of the stack at this point, right? This one is pretty easy. What's happening right now? Yeah, we simply XOR with the same register value. Effectively, we assign 0 to ECX and push ECX on top of the stack, meaning that we just assign 0 value on top of the stack, right? See how this stack change after we execute this one. And then push ECX. ECX now contains 0 value. And then top of our stack, we have 0, right? Anyone has a good guess what would be the value, why we put the 0 inside the stack? What's the use of those later? It will be the value for EMVP, but other than that, the last element of the argument vector. We'll locate it here. Likely, we're going to put a pointer to the shell to on top of the stack so that we have corresponding argument vectors. So we're going to pass to the exec v, right? Anyone can explain the next line? Push, pop. We simply move the value 4 to ECX. Why not just calling move? Any idea why we are not just calling move? What do you say? Yes, there will be a lot of zero if you ended up moving zero value to ECX, right? So this simple trick of push and pop not only reduce down the amount of character and bytes they require, just one byte each, you can push and pop, right? It's a pretty convenient way you can assign certain constant to the register value. Now ECX contains 4. What they are doing after here, the add. He add up the stack pointer with constant 4, meaning that you're pointing to the next value on top of the stack, right? Top of the stack is ESP, and ESP plus 4 effectively. Now ECX is pointing right next to the element on top of the stack. And then we're going to push ECX, which happen to be the pointer to the point to the shell, and we're going to push on top of the stack as well. Okay, let's see how it works. Check the stack frame, right? We're going to push 4, so we have a 4 on top of the stack. We're going to pop, so ECX now contains 4. We're going to do pointer manipulations. So we're going to add up 4 to the stack frame, and ECX now pointing to this guy, which is shell. Right, now have address pointing to the shell. We're going to push this pointer on top of the stack. Right? So we now have argument vector on top of the stack. Now we have 2 arguments inside arg v. First one is a pointer pointing to the shell. The second, we have null to indicate the end of the vector in exec-cv system call. Right? Is everyone on the same page? Not? Okay. Can anyone explain this 2 line? Yes? What is a stack pointer? Pointer to argument vector, right? So we now have a pointer to the argument vector, which contain the pointer to the shell and null pointer as their argument. So we now have instruction the stack pointer that can be used of the argument of the exec-cv as a result of this operation, right? See, we're gonna copy the stack pointer to the ECX. ECX pointing here, which have 2 elements. The first element is pointing to the shell. The second element is a null pointer, which just indicate the end of the argument, right? The ECX now has a proper value for the system calls. Can anyone explain next two line? Pretty easy. What exactly B? What? Yeah, 11. Syscall number to exec V, CVE, right? So let's proceed. Push B on top of the stack and pop EAX. We are now ready to invoke the exec V CVE system call, right? The first argument is path, now pointing to the bean shell on top of the stack. The second argument is argument vector, which pointing to the array, the list of elements. First one is pointing to the shell, second one is null. Interestingly, environment variable pointer can be just null, so that it ignores the environment variable as part of this system call, right? If you execute this, the program will launch the shell as a result, right? This is how you debug the system calls, debug the shell code from the shellcraft as well. And then as part of our exploit, we're going to utilize this shell code. And okay, here we're going to put the shell code right after. In order to do this, you can say assembly and shellcraft Linux and shell. But you can specify shellcraft.i386 and whatnot. In fact, you can specify my context pretty easily in Pwntools. Here you can say my architecture that I'm working on is this. Is a 32-bit architecture in x86, so that you can just specify I like to invoke the bean. I like to get the shellcode for the Linux platform, and I will just invoke the shell. So in here, what's going to happen here is that, let me copy this one. In fact, this one is actually just a string, right? It's the sequence of assembly, so that you can print out the shellcode like those. If you want, you can compile this shellcode with the assembly. Or if you want, you can hexadump the entire things so that you can see what's going on. Here, we provide we got the shellcode out of this shellcraft.linux.sh. We return the string, the actual assembly. And then we're going to compile with the assembly functions provided by Pwntools. And then we're going to dump the entire binary as it is, as a hexa dump. And then we're going to append the binary of the shellcode as part of our input space. Okay, let's execute this one. So as you can see, this is the shellcode that we got from the shellcraft.linux.sh. And this is compilation of the previous assembly. And we provided this as a part of our exploit so that this crash might contain the shellcode, right? If you launch the GDB core, you can see instruction pointer is overwritten to that beef. But at the same time, the stack pointer pointing to what are those? Any idea? Shellcode, right? This is a buffer that we put it in, the payload that we appended right after the overriding of the return address, right? Because we appended the shellcode at the end of our input, right after the return address. You can see, push the 68, which is the end of H, right? The sequence of system call. What should we do? We know the location of the shellcode. Just copy this guy. Say return address. Okay. We fill the buffer. We change the return address to this location of the shellcode. We injected the shellcode that we got directly from the shellcraft. Okay, let's try running this one. Okay, crash instead of getting the shellcode. Let's see what's happening here. On top of the stack, this location, we still have proper shellcode injected, right? But this instruction pointer is crashing at the moment. Okay. It means the program is executed for about, say, 41 bytes, but it stopped. It stopped at the particular locations that we have. Return F. Any idea what's happening in this exploit? So from just 10 instruction pointer, if you disassembly 10, it seems like pretty legitimate, right? It's a shellcode that we injected to the program. You can recognize pop 4 and push 4 and pop ECX, right? But if you dump more and more, you recognize something different. Is there anyone who recognizes the differences between the shellcode that we injected here and we created? Could you explain once more? Here, right? This is not the shellcode that we injected, right? What's the difference between these two? What do we have instead? Push B instead of 0. It seems like rest of the instructions also ignore in this case. Anyone has a good guess what's happening in this exploitation? Yes?
Yeah. System calls stop ingesting buffer.
Basically, the scanf return not the entire input that we provided. It stopped accepting the character at the B, right? In fact, we couldn't inject the entire shellcode to the program because of the limitations of the scanf. What's special about this B? What do you say? So, no, it's not white space. Yeah, there is a special list of the special characters that scanf treats slightly differently from normal space. By definition, scanf accept the character until you see the new line, right? You can even inject the null if you want. But in this case, these are the special character. You can check every single one of them by yourself, starting from, I guess, backspace, holding, line feed, virtual terminal, and stuff. And these are the special character that scanf will stop accepting more character if you ever see those type of characters in your input, right? How can you avoid? How can you avoid these characters in our shellcode? Any idea? What do you say? Yeah, how to not entering this number?
Shellcraft has a prologue. Python library is so I string.
Okay. Well, anything you can do manually? Yes. Yeah. So, any good suggestion for this particular exploit? So let's copy this shell instead of getting everything here. Let's write everything by ourselves. What should be the modification of this shellcode? What do you say? Yeah, that's a one way. So instead of inserting this 1b, what you're suggesting is that push maybe 1b, 10 is tricky, 3b, pop, subtract, 30. Does it provide pop, push, subtract? So EAX will get the proper system call number at the end? I think likely. Nothing special about those. It seems like it's working, right? So by providing those, what we just did here, instead of using the B, we provide a little bit larger number so that we can avoid these special characters. We push. When you're pop, you still have these larger numbers, but you can do simple arithmetic on top. Luckily, this particular shellcode doesn't contain anything special about a special character that scanf3, right? So we can write the shellcode. This is one way you can utilize a shellcraft. Another method that I like to share together is that if you want to write the system code by yourself, in fact, you can also leverage what shellcraft provide. Instead of invoking the shell, what I like to do, I like to open the proc flag, read, and write after all, right? So that we can really dump the proc flag to the output of this shellcode instead of launching the bin shell as a result. In fact, in this job, you have to invoke 3 different system calls: open, and read of the proc flag, and write it to the terminal, right? In fact, you can do all these things pretty easily by using shellcraft. Okay. If you dump the list of program, the shellcode that you can utilize these, in fact, it is open, right? You can see system call open. You have system call read here, and then you also have a system call write as well, right? And these are the list of the functions that we like to chain together as part of a shellcode, right? Let's try the execution of this. Say Linux open. This is a simple open list of instructions that invoke this open. But in order to adjust the first argument of open that point to the proc flag, you have to provide the argument. Here, say I like to provide the proc flag as the first argument of the open system call in this way. And then we like to read. I like to provide the read-only argument to the O flag, which is the second argument of the open, right? And in fact, this one is actually open the system call, actually open the proc flag. In order to verify their executions, in fact, you can do debug, provide the debugging method, right? And then here you can execute step by step until the system calls. Your first argument is a proc flag, the pointer to the proc flag. Second argument is 0, is indicate the O read only. And then the third argument is 0 as well. So if you execute these functions, you can see the file descriptor that opened by this program doesn't have files. Another way is that this is a process number. In your Linux systems, you can actually navigate pretty easily what's the open system call. So if you type proc info, typically there is a list of file descriptor you can check. For some reason it doesn't work. It doesn't matter. Process ID. Then you can see list of the file listed. Here, it has a file descriptor 0 to 3. 3 actually pointing to the proc flag, meaning the file descriptor 3 is correctly open because of the system calls. And if you're using the number 3, you can read the proc flag as a result, right? This one is executed pretty well. So let's use this system call in our shellcode, right? Remove this guy. Next, we first gonna open the proc flag, and then we're gonna provide read-only argument. Again, these are just a string, so that we can keep concatenate what we want to do. Because we just successfully opened the proc flag to the file descriptor 3, which is contained in the EAX register, right? Next task is just read those files through the file descriptor. Similarly, you can do Linux read. What would be the first argument? You can do constant 3, or more universally, you can do EAX. If you provide this EAX, then they pick up the register, start reusing the value inside the EAX. What would be the second argument? Pointer to the buffer. Where should we put whatever we are reading? Any idea? Any good location to put data? What do you say? ESP is a pretty good location. So let's put the data to ESP. How much bytes should we read? What's the size of the proc flag? It's about 1,000. Maybe put random number. And then we're gonna, after we read the buffer, and we're gonna write back to the console output. What would be the first argument of the write? What? 1 is a standard output. What would be the second argument? ESP, the buffer that contained the proc flag, same size. So let's execute this guy. Okay. Apparently we didn't get anything. Any idea why it got crashed? GDB core. It seems our stack contains something, right? Do you see the familiar characters on top of the stack? Yeah, in fact, this is the contents of the proc flag. We actually read correctly. Apparently, we didn't print it out. Instead, it crashed, right? Why is it crashing? Can you check the instruction pointer here? Instruction pointer pointing to somewhere, which contain, as you can see here, is just a ASCII character, right? If you try to disassemble this guy, in fact, it seems like legitimate instruction, but in fact, it's actually part of the proc flag. What exactly happened right now? Yes? Exactly. So you put the shellcode on top of the stack, right? You override the return assertion correctly, but we are using the instruction pointer. No, we are using the stack pointer pointing to the stack, which ended up overriding the shellcode that we put it to the stack as well. So keep overriding, starting from the top of the stack all the way down. What would be the good place that we can put correctly in this target binary? Any idea? Yes? Oh, that's a good approach. Basically, what he's suggesting, instead of letting this proc flag override something, what about we create a bunch of nope at top of the stack, so that while executing it's completely fine. When you're overriding, it might override the nope, which don't care, right? I think that's another way, right? Let's try. I think that should just work. Do you guys know what's the opcode for the nope? Yeah, or you can just type this. 40 is what we are aiming. So basically we create, right after overriding return value, we have a bunch of uninteresting places. When you're executing, it's completely fine. When you're at the moment that you're overriding them, it doesn't matter, right? Yeah, we got the shellcode. Oh, shoot. It's completely exited. Fine. Any other way we can pick the right place? This is a good approach so that we can avoid the overriding of our shellcode itself. Is there any place we can place the shellcode better than ESP? There are multiple places you can inject. Any other idea? The simpler way, I would say not simpler, but so program crash. This is a memory map of the process, right? It seems there's nothing you can override it here, but let's try with the GDB so that you have a better idea of the stack space, memory space well. In order to do this, what you can do, you can attach the process to the GDB as part of the script as well. So I'm gonna invoke gdb.attach. It's only work in your local machines. We're gonna attach our process here. Say, so we're gonna attach to the process, and these are the GDB command you can inject as part of this script as well. Say hello. You can put anything or not putting anything as well. Let's see we can do. We launch the process, we attach the GDB, we pause. We can continue to execute if you want, right? And process crash because of overwritten instructions on top of the stack. If you type vmap, any other interesting place you want to override? Do you see the right permissions in some memory space? This is better, right? The first two memory map, it seems like with only memory regions and executable, likely the code sections. But what about the third? These are the data sections you can override. In fact, because you can see these are RWXP, these are the permissions of this memory map. In fact, these are the regions you can easily override anything you want. Pick any place, right? Say what's inside. In fact, there are a lot of interesting stuff which are the good target for our later exploitations. But you can pick something in the middle, right? I don't know, I pick just a random place and mostly not used. What about we put this address to our program? Okay. You can say buffer address. So instead of ESP, you can say buffer address and buffer address. Okay. We run. Continue to run. You can see the entire thing is printed in the right side. Let's see what's inside this buffer. These are the string, the content of the proc flag file, right? So by providing this unused memory space, we could read entire content from the proc flag and dump it to the shell, right? Another method also you can do. In fact, you can modify this shellcode pretty easily. Instead of putting everything to the beginning of the stack, what about we move the stack a little bit up so that we can lift the stack to way beyond, which is not usable space, that we can start putting the proc flag way beyond the stack pointer. So one way you can do is say buffer address stick to the ESP, but we can manipulate right before putting here. You can say subtraction ESP, put the constant, right? Again, these are the assembly string, so that you can put whatever string on the middle. Here, after we read, open the proc flag file, we manipulate the ESP, so the ESP now pointing way up, so that even if you read, it still still not touching the shellcode that you injected, right? So keep adding this GDB is annoying, right? Then you can provide no ptrace argument to this shell2 script. Then it ignores the execution of the GDB, right? Here you now execute everything without GDB. Now still get this shellcode running, so that you can get the proc flag as well. So we know we just craft proper shellcode to attack the binary in my local systems. What would be the next step if there is a binary in the server side? Yeah, you can communicate the connections, communicate to the server, or better approach, you can copy everything to the server and see if it's working, right? What would be the challenges of copying this shellcode to the server side? If you just run this one to the server, it's gonna work? Have you tried? Data section is exactly the same, but what are the differences between my local environment and the server? Environment variables are different. So what are the things that we adjust in this shellcode? Yeah, return address. Luckily, our environment provide our server provide a way you can browse the core dump, right? That you can easily identify the corresponding return address and stack pointer and whatnot. What if we don't have? Let me show you how we can manipulate how we can write the shellcode much reliable way, right? In order to do this, we're gonna do. There is SSH session you can create on top of the Pwntools as well. You can simply invoke SSH and the user ID and whatever 6265 address. Then you're gonna have the session to this server. You can put the IP address. I just create the name for this one, or you can provide the password after. So in my case, in order to not revealing the password, I just install my SSH key to the server, so I can just invoke here. Otherwise, you have to provide the password as well. I think you can provide the password with the password argument like those, right? So we got the session, and then we can create the process by using this simple command, the process, right? Say, I like to execute. You can provide the actual path name, tutorial 3, Pwntools, right? And then we have to provide the working directory. In this case, say tesu. So let's remove all those. Say I just create the session. I just invoke the process I just provide the name of the process's path name and current working directory. So you can put any directories under temp. Let's see it actually connect to the server. Right? Oh, 6265. Ah, there's no pay. What? Oh, cannot find the. So you have to create this directory. So here there's nothing inside. We're gonna run this program. Hopefully connect. Let's connect to the server, invoke the binary under this current directory, and you can see how things are interacting. Here we provide a payload itself, which unlikely the program is gonna crash, although we modify the return address, right? Because some of the differences between my environment and their environment. But we still provide the payload to the server. In this case, program likely crash. You can see in this directory, the core dump is provided for the debugging purpose. In this case, what are the things that you're gonna do? Check this one. And we are looking for have you recognized any interesting place? Here. These are the instruction pointer that we override for sure. What about the stack address? These are the stack address. Should we jump here? It seems like the beginning of the stack address, right? Should we jump here? See, let's keep this return address just in case we like to debug. See, we change the return address that meet the environment variables inside the server side. We can replay the same attack through the script. But it's lame. We have a different type. We have to modify all these depending on the target. So I like to show you how can we write much more reliable exploit against this binary, assuming that you don't have any access to the core dump or information of the core in the server side, right? You guys have any suggestion how to improve the reliability of this exploit? What would be the better way? Yeah, you can create an obsolete, assuming that you don't have any idea of, I would say, environment variable that they are using. How to synchronize two systems as much as possible. Yes? Yeah, we can eliminate the entire environment variable so that at least, although there's subtle differences between them, even if you completely eliminate environment variable. For example, do you guys know the what's in the beginning of the stack when you launch the program? You guys know? Say Pwntools. Say we start the program and these are the stack. What's in the bottom of the stack? Say maybe some value. Can you recognize? So these are the bottom of the stack, right? Anything you're recognizing here? What are those? These are two null characters at the end. It's really the bottom of the stack. What are those? until here? It's a program name. So when process is launched, on the bottom of the stack, they're going to put the null, the 8 bytes of null, to indicate the end of the stack. And then they're going to provide the actual name right after. And on top of them, they're going to construct, I would say, auxiliary vector, which is necessary meta information for the process. And then they're going to create they're going to put the environment variables, and also they're going to put they're going to create the array of the argument and environment variable pointer that will be used by the main process, main function that developer wrote, right? But when process is launched, these are the basic setup, right? In fact, these are the non-deterministic source of your program, but in most, you can eliminate the large part of environment variable so that you can make both stack very similar. So we first gonna eliminate the environment variable. How we can do? Any idea? In fact, environment variable can be completely controlled by the user of the process. Here you can provide env as an argument, and we put environment variable to empty. Similarly, in local setting, you can say environment variable to empty in this way, right? We first have to debug the process inside the local environment before we actually interacting with the server side, right? One trick that I'm using all the time is that instead of keep uncommenting those, say if we define this remote in my environment variable, I'm gonna invoke this. Otherwise, I just gonna invoke this guy. Okay, let's first execute this one in my local setting. No ptrace. Okay, let's first change. What was the local set? This was a local, right? Remove this. Crash. What's happening? Any idea? We expect that we remove the environment variable. Hopefully we run those. What about we just remove this environment variable? It's gonna work? Oh. Okay. Make sure this is running, not running. The path is changed because we run this tmux core. Oh. So I just changed the instruction pointer in the return so that we can debug the location of here. This is the beginning of our shellcode. Just slightly change it, right? Hopefully we get the shellcode, right? So shellcode is running, we verified it. So what if we change the environment variable immediately after? So we set the empty environment variable for the shell SSH session. We also put empty to the local setting here, right? So we're gonna execute without trace, without ptrace, it crashed. What's going on? We just changed the environment variable. Any idea what's happening? Because we eliminate the environment variable, the entire use of the stack is squashed. So that the shellcode that you previously injected is not true anymore. So you have to do this process again to find out the right location of the shell stack, right? Here, it's probably everything is slightly changed because of something happened in this particular location of the the top of the stack. I think better way is just, again, you can either attach the GDB or you can slightly change the return address to something that you can check. Crash, and we now the beginning of the stack, right? Stack a little bit change, right? And this is address after we setting the environment variable to 0, right? If you execute this one, it just, of course, it works. But this is time to make a trick, right? We remove all the environment variable so that we can execute things in more reliable way. Instead of pointing out the exact locations of, I'll say, buffer, the shellcode, it's a time to create the nope sled, right? As part of our shellcode, we're going to put humongous amount of the nope sled. Hopefully, we can jump in the middle of nope sled so that you can continue to execute after. So one way we can do is that after this return address, we're going to put the nope. We say thousands of nope. Sounds enough, right? Because we put the nope, we can change the return address. So instead of executing, starting from the buffer that you injected, in fact, you can jump in the middle of the nope sled. In this case, you can calculate pretty easily. You can add up so that you can go further in the middle of the shellcode by simple pointer arithmetic. In this case, we put about thousands of the nope. Let's jump in the middle. In this case, 500, right? So instead of executing the shellcode at the beginning of the buffer, we're gonna start in the middle. If there's a subtle changes in the location of the shellcode, it's still okay because we have large buffer between and after. This is the nope sled that we created, right? If you run this one, unfortunately, it doesn't work. Any guess what's happening? What about we put the GDB? And then let's continue to execute, but stop here. What exactly happening? It stopped in the scanf call, as you can see here, right? BFS scanf, the one of the functions in the libc. But the crash in this particular location, so instead of executing my shellcode, right? The scanf is actually stuck. It's not even going further. What's happening? Any idea? No one? And this is the instruction they're using. They're copying something to the EDX. EDX pointing to. Can you recognize what's the location of this? Yeah, end of the stack, the bottom of the stack. So in fact, there's enough memory that you can override. In other words, your shellcode is way too big, right? Because of the nope sled. And you ended up having too many bytes that you're using for the reliability, but you ended up overriding entire of the stack because of this large humongous value, right? How to avoid? How to enlarge my stack? But without introducing any differences between these two server and my local environment. Any good way to introduce large buffer for my large input? In fact, you can put a lot of consistent value to this environment variable. Because we are using more value in the stack in our input. In fact, you can, instead of shrinking everything down, you can actually put something in the environment variable, right? As far as it's consistent across my computer and the server, that's completely fine, right? In here, instead of putting empty environment variable, we're gonna put, say, very large. Hopefully, it's enough for the nope sled, right? So we put this large amount, okay? what about we put this nice value? And then because we put this amount of invalid variable, what would be the stack address that we have to change? Or you can check different way, but likely you can just adjust D to other. And execute, we still, oh, it was not right. We still got the crash in executing the certain locations, but let's figure out the correct, the beginning of the shellcode that we can modify the return address, right? Here, but at least we're not crashing in the scanf, but we're gonna put the return address to that beef that we have expected. Ptrace crash, and this is the beginning of the stack. Where's ESP? This guy. Return address would be this guy. Oh, I calculate incorrectly. This is the amount of no code that we injected, right? But instead of using the exact locations like this, right? We adjust the instruction pointer that point to the middle of the shellcode, right? Middle of the NOP slide. But not exactly after the shellcode or beginning, it's really the middle. Entire NOP code is just one byte. In fact, you can put any places in the middle, and even if there is some differences in the stack, you can still execute correctly in this way. Okay, let's execute. Hopefully we can get this time. Yes. We got the shellcode here, and each time to actually use the exact same shellcode to attack the remote side. Okay, in order to do this, we just provide the remote. Hopefully we can get, yes. So we use the same payload and same execution logic between my server and my local environment, so that we still get the same flag out of the shellcode that we create. Okay, that's all for today. And your job today is actually replicate what I have been playing with in today's lecture. And hopefully you can really solve this week's challenges after solving this tutorial. And we're here to help. If you have any questions, feel free to ask as well. Okay, thank you so much. Yes, if you have any question.
Store shellcode.
Yeah, that's another trick that you can do. What do you say?
You want to show us?
Yeah, it's the same thing. Okay, let me. Okay, what about we put shellcode here instead of C, right? So one trick is that do not introduce too much differences between my local and server side, right? So let me just first crash or attach the GDB when we are executing this guy, right? It stopped. What about we pause right before, or I think we can just execute and still search. Let's see. Here, start. But we like to know the location of the C, right? This is where the beginning of my shellcode. There's so many. It seems like this is a location, right? What about something before? Oops. I'm looking for BBB as well. Ooh, no B. Okay, no B. Let's see. I just want to verify the exact location, right? So I like to search the DDD location. Then continue. Only BBB. Okay, let's set the breakpoint here so that we are not actually overriding anything, so that we can examine more. Instead of crashing it, we just want to pause, right? So I set the breakpoint here and continue to execute. So I don't have to keep typing. Okay, so let's search DDD. What? There's no DDD. Okay. Did I put 3D? Yeah. Search. At least we have CCC. See. I think it doesn't matter. We can just use this one. So, why DDD doesn't exist? Okay, or we can say, so the end of the strings are all invalid variable, right? Here, so compare the address. So we have about thousands, right? Right, no slide. Why start execute from disk? We don't have enough space. Okay, so this is the end of the string. You can manipulate, right? Here minus. Why we have all the nope? Why no indeed? Interesting. Why we have all this no? Interesting. Let's just execute. What did you say? 1000 no? Where? No, I'm looking for the invalid variable that pointed here. So what I want to do is to provide this invalid variable in these locations. I want to see this DDD and CCC are consistently located there. But it's because we override all these nope slash all the way down here, so it doesn't matter. We just provide too many input to the program, right? So here, instead of providing this, because we don't need anymore, right? It doesn't change anything, but we still get those informations. Here we can search DDD now. See? That's why we have so much nope load overrided here. Right? Right after this, you have like CCC, and these are the locations that you might want to use the shellcode, right? And so instead of putting the shell like here, what about say payroll 2? Say we first gonna put the nope. Not sure it's a good idea because it changed here. So I think just ignore the shellcode. Just put the shellcode here. payload 2. But instead, we're going to put the shellcode in payload 2. But this is a tricky part. Assuming that you have all the character right in the payload 2, and then we like to still keep the same thing, right? So that we still put the same things as part of the environment variable. And when you're jumping, you can jump here. And you can create some of the nope if you want. Maybe hundreds of them. Put here. When you're jumping to return address, you can put here, right? So hopefully we can jump in the middle of the node. In this case, instead of 100, I'm going to provide 50, right? So this was user locations and return address. See? Oh. Yeah. Unfortunately, there is a null. You have to eliminate this null in your shellcode, right? That's unfortunate, but you can try.